So what's the general problem here? So we have, so you have a bunch of, so this is the context in which people normally see hashing. Okay, so you have a collection of unknown strings. Okay, so think of them as strings of certain length. And you want to map these strings into significantly shorter strings. Okay, so that the mapping is roughly 1-to-1. Okay, so you have strings of length n. So this is S of length n, and and you want to map them into strings of length k, and you want a roughly 1-to-1 map. Okay? So you might say, how is this possible, right? Because you have 2 to the n strings on the left, and you have only 2 to the k strings on the right. Okay? So we're thinking of k as much smaller than n. Okay? But the point is that we don't have all the strings here. Okay? We just have a small number of strings here. Okay? So think of in the interesting case, we have all these n-bit strings, but we have only like, let's say 2 to the k of them, okay? Or roughly 2 to the k of them. And we want to map them into k-bit strings. Okay? So this is the kind of situation where which we'll be interested in. And the thing we'll analyze now is the point of random maps. Okay, so suppose every string on the left is randomly mapped to some string on the right. Okay. We're going to analyze what kind of properties this random map has. Okay. So is what we are going to analyze clear? So one thing to bear in mind is how to construct such a hash function is a different problem, and it's usually non-trivial. Okay, so if you have a long string, how do you quickly come up with a hash that maps to a uniformly random string here? That's an interesting problem in itself. And it's not so difficult. We'll see examples in the homework, but it's not trivial. But for now, we don't worry about it, and we always just think of being able to do that. Okay, so this is the situation we will analyze. Alright, so let's make this simpler. Okay. So strings are messy to deal with. So let's think of, suppose you have a collection of n integers in the range 1 through capital N. Okay. So you have n integers a1, a2 up to some a small n, and they're all in this range 1 through capital N. And we want to hash them into what are called buckets. Okay, so think of a bucket as being something like this. It's a sideways growing bucket. Okay, and each one goes into a random bucket. Maybe 2 guys go into this, and so on. So this is a very simple process, right? So you have n numbers, and we are just throwing them into random buckets. And and initially I'm starting off by assuming there are exactly n buckets as well. B1, B2 up to Bn. Okay. So this sort of thing is sometimes called balls and bins. This kind of a setup. Okay, so you have n balls and you're throwing them into a bunch of n bins. Alright, so what are the kind of questions we care about? So in this setting, you could say, what's the expected size of a given bucket? Okay, so you could say, how many balls end up in bucket 5 in expectation? Okay, so that's a reasonable question to ask. And we might be interested to ask, okay, will there be a collision with good probability? A collision usually means 2 balls going into the same bucket. The reason this is interesting is again from this hash function point of view. So if you have these strings that map to the same thing, so you don't want 2 strings mapping to the same hash. Okay, so that's why it's called a collision. Okay, so collisions are usually bad. And we'll try to see will there be collision. And you could also say what's the size of the largest bucket. Okay, so that's again something that we care about. So how many of you have seen the answer to this last question? So what is the size of the largest bucket if you do this sort of a random assignment? Just to get a sense of, I don't expect most of you to have seen it, but I'm just curious.
N.
Sorry?
N.
Okay, so that's incorrect, but yeah. So we'll see that it's not n, it's much smaller. I mean, in fact, if you have n things and n buckets, right? N balls and n bins. If you throw them randomly, my initial guess would be like a constant, right? Because
but n would be the worst case scenario, right?
n would be really a worst case scenario. So what we are interested in is what is the, I guess I should be more formal. I should say that what is the expected size of the largest bucket. Okay, so what is the expected size of the largest bucket? Sorry?
Log, I think.
Yeah, so for all these things, you know, if you had to guess something which is a little bit bigger than 1, you would guess log, right? So that's the thing. So the expected size of the max bucket, it turns out to be roughly log n. Okay, so this is like log n over log n. And this is actually pretty tight. Okay, so we'll see why that is true. And so if you throw randomly, we also, I mean, so one thing which is easy to see is in expectation you think that every bin or every bucket gets one element, right? Because there are n balls being thrown into n bins, so in expectation everyone should get one. So that we'll try to analyze. You might also ask, okay, how many bins are actually empty? Okay, so if you do this, do you expect, I don't know, n over 5 bins to be completely empty? So you would not intuitively, but it turns out it's true. Okay, so we will see that also. All right. So let's try to see how you approach these kind of questions. Okay, so in the process we'll see some pretty broadly applicable techniques. Okay, so first is expected size of one bucket. So I will use the words bucket and bin interchangeably. So let's fix some bucket. Okay, so let's say I fix bucket B2 or B1 just for convenience. And what is, I'm asking what is expected size of bucket B1. So how would you go about reasoning about this?
You have the probability of 1 over n, put 1 volts in it each time.
Yes, so I guess what you're suggesting is to compute the expectation, what I have to do is I have to compute what is the probability that I put exactly I balls in it. Okay, so this is the probability that I balls fall into B1. And then the expected value of the size of B1 is sum over I equals 1 through or 0 through n I times the PR. So this is just the definition of the expectation. So you can say, okay, I can compute this PI for every I, and I can compute this quantity. Okay. So this turns out you can do it, but this sort of calculations become messy. Okay, so you can see. Okay, so what is the probability that there are exactly I balls that fall into this? Okay, so you could say, okay, so there are n balls total. So I want so there are n balls total. And I want exactly I of them to go into B1. Okay. So for one ball, okay, so for let's say the jth ball, probability that it goes into B1 of all the buckets is exactly 1 by n. Okay. So if you pick any given collection of I different balls, then each one has a 1 over n probability. They're all independent. Okay. So the probability that all of them go to B1 is 1 over n to the I. Okay. So hopefully that is clear. And then you have many ways of picking I different balls. Right? So you can say that this is n choose I times 1 over n to the I, and then you sum, that is equal to Pi. And then you can sum this up over all I. But you can see, right, I mean, maybe some of you are good at this sort of manipulation and you can do it, but this sort of thing it's messy, right? You have to do some algebra, you have to figure out what's going on. Okay? So it turns out there's a very sleek way of doing this sort of calculation. Okay? And that is by defining appropriate random variables and just viewing this as a sum of random variables. Okay, so let's see that. So let's define xij. So in this case I don't even care about xij. Let's just write xj. So this is the random variable. Yeah, this is a 0 or 1 random variable. So it's 0 if j goes to any bin apart from B1. And it's 1 if j goes to B1. So this is a perfectly legitimate random variable. So random variable is basically, it's some real valued function which depends on the assignment. Okay, so if you, after you made your random choices, this will evaluate to either 0 or 1. Okay, so this is a random variable. Now, how can we write the size of Bi? So sorry, how can we write the size of B1? Suppose you defined all these random variables. Is there a way to write the size of B1 in terms of these random variables? Yeah, so does everyone see this? So xj is either 0 or 1 depending on whether j is in B1 or not. So the size of B1 is exactly the number of xj's that are equal to 1. And so in other words, it's just the sum of the xj. Sum over j equals 1 through n of xj. Okay. So this is what we have. And now you can say, okay, so I want the expectation of the sum of quantities. Yeah?
Isn't this just dividing n by?
Dividing what?
The answer will be 1, right?
Yes, but formally if you want to say what's the expectation, right? So, in this case it's intuitively clear, but there are cases where, you might have to think more carefully about what's going on. But here also, it's not, actually what I wrote here is also different, but yeah, so in this case it's easy, but there could be cases where it's not trivial. Okay, so yeah, so actually, by the way, so what I wrote here in this right is a little bit wrong. It should be times 1 minus 1 over n to the n minus I, but let's not get there. Okay, so that was anyway a complicated calculation. So the reason you conclude it's 1 is a very intuitive one, right? So why would you say that?
Because the expectation of xj is 1 by n, and n times when you're choosing xj is going to be 1.
Right, so that's what I'm going to get to. So what you are implicitly using is what is called the linearity of expectation. So if you have a sum of random variables, okay, their expectation is the sum of the expectations of these random variables. Okay, so we'll see that, that's what I'll write in the next slide. But first, is it clear that B1 is sum over j of xj? Okay, so this is obvious, right? So it's just the number of xj's that are equal to 1. This is by definition. So now what we are interested in is the expected value of sum over j equals 1 through n of xj. And yeah, so what the linearity of expectation theorem says, so the point is that this is a very general theorem. Okay, so this is true for any random variables that take the same, that take values in the same domain. So if you have expected value of this, then this is equal to sum over j equals 1 through n of expected value of xj. Okay. So in your homework you'll see a problem where if you try to do this without using this, I mean you might be able to if you are really good at manipulations, but otherwise it will be very difficult. Okay, so I mean if you try to use the definition of the probabilities and so on, it's going to be very messy. Okay. So in this case it's relatively easy, and let me state this formally. Okay, so for any real valued random variables, A and B, you have expected value of A plus B B. And yeah, the proof of this is relatively straightforward, but it's if you try to work it out from the definition, it's a little bit tricky. Okay, so you have to view this the right way. Okay, so we won't go into the proof of this, but this is something that's very useful. Okay, so this is called linearity of expectation. Okay. And this is true for any real valued random variable A and B. So now we have this, and this turns out to be fairly easy. So now all we have to do is find the expectation of xj, right? And for a given j, what is the expected value of xj? So remember, xj was this, right? It was 0 if you go to any other thing, and it was 1 with if j went to b1. Okay. So what is expected value of xj? Yeah, so it's 0 with probability 1 minus 1 over n plus 1 with probability 1 by n. Okay, so this is 1 by n. So this is just a simple calculator. And because of this, you just have expected value of size of bi to be equal to n times 1 over n, which is 1. Okay, because the sum has n terms. Each one is 1 by n, so it's 1. Okay, so this is the expected size of one bucket. Okay, so the nice way to calculate this is just by using this trick called the linearity of expectation. So this is the solution. Okay. All right. So this says that in expectation, each bin has size 1. Okay, so that's the expected size of each bin. Okay, so what about collisions? Okay, so collisions are bins, two different balls that go into the same bin. Okay, so that's when we say there exists a collision. So another way to formulate this is how many bins get two different balls? So you have n different balls to start with and n bins. Each one goes into a random bin. So what would you expect this this number to be? So, actually, initially you could even ask, what is the likelihood, what is the probability that there is even a collision? Okay. So, multiple questions you can ask here. That there exists a collision. So let's maybe try to answer this first. Okay. So how would you answer, what's the probability that there exists a collision? So is everyone clear on what a collision is, by the way? There's two things hashing to the same thing. What's the collision? Yeah.
You can do it with markers and equality where your expectation is 1. So the expectation of the size of any bucket is 2. So it's 1 by 2. Right?
So it's at most 1/2,
Yeah.
right? So you get that, what that implies is that there are at most n by 2 balls that have size 2. But that's not what I'm asking. What I'm asking is, what is the probability that there exists a bin that has two, yeah.
So maybe take it from the perspective of one bin and say what's the probability that the first ball goes in that bin, the second ball, and so forth. If
Okay.
you run across each ball, then
Yeah, so that is one way of saying it. So you could say, okay, look at one bin. Okay. What is the probability that there exist two different balls that go into this bin? Okay, so this you can try to compute, right? So you could say this is one bin. So this let's call this B1. And what's the probability that there exist two different things? And here again you could do the kind of calculation we did before. Okay, so you could say, what's the, I pick all possible pairs of these two bins, of these two balls, and say what's the likelihood that this goes into this and this goes into this. And you get some summation like this, right? So you get, you have n choose two such choices. For each one it's 1 by n squared. 1 by n squared because this has to hash to that and this has to hash to that. Okay. And n choose 2 is because that's the number of things that you have. And this, it turns out, this is actually, this is roughly half. Okay. So what you said is kind of correct in the sense that if I take any bin, and I ask what's the probability that there are at least two, then you get something reasonably close to half. Okay. So you do expect that there are plenty of bins that get at least two things. Okay. So is this clear? So there are a fair number of bins that get at least two things. Okay. So the probability that there exists a collision, you do expect it to be quite big. Okay. So what I'm asking here is, does there exist even one bin that has two points? Right? And what this is saying is that I actually expect a lot of bins, because the probability that one specific bin has two balls is at least half. Okay, is around half. So that's why you expect there to be a lot of bins. So you can actually work this out, and the right way to work out these kind of probabilities is to, sometimes when you're trying to compute the probability of an event, it helps to compute the probability of its negation. Okay. So this is one standard trick in probability. Okay. So you could ask, what is the probability that there is no collision? There is no collision. What does no collision mean, right? So it means there are n balls and there are n things. Each one goes to a different way. So this I think was in homework 0. So those of you who solved it will know. So what we are asking for is, there are total of n to the n assignments, and of those we are asking how many are permutations, right, in some sense. So what we are saying is, what's the likelihood that exactly one goes to each thing? So the resulting assignment you get is exactly like a permutation. Okay. So it turns out, if you don't see this, you can think about it for a minute and you'll see this. Turns out that this probability is something like, it's actually exactly equal to n factorial divided by n to the n. Okay, so n factorial is the number of permutations. This is the number of valid things in some sense. Okay, so this is when there is no collision, and this is the total number of mappings that are possible. Yeah.
I think I just missed out on a detail. Is little n the number of balls?
Yes.
And
So it's actually both sides are n for now.
so little n is both the number of balls and the number of things.
Yes. So otherwise these calculations will become a little more messy. So that's why I want the simplest case. Okay. So this is the probability that there is no collision. This turns out actually is something like 1 over e to the n. Okay, so for this is what's called Stirling's approximation. So it turns out n factorial is exponentially smaller than n to the n. Okay? So the probability that there is no collision is exponentially small in n. Okay? So with extremely high probability there will actually be collisions, but there won't be too many of them. So what this says is you will find bins that have 2 balls with really high probability. Yeah. So that's what this is saying. So even though the expectation for every bin is equal to 1, okay, so there is supposed to be, with very high probability some kind of an uneven distribution. So that's what this is saying. Okay. So this is just a collision argument. So now this also leads us to this question of, okay, so if I had n balls going into n bins, then there was with extremely high probability a collision, right? So you could say, what if I had much fewer balls? Okay, what if I had n divided by 100 balls? And these were going into n bins. Okay. Would there still be collisions with good probability? Okay, so what's your guess? You had n over 100 balls going randomly into this bigger space, right? So would there still be collisions with good probability?
Yes.
Okay, so there seems to be a decent split between answers, right? So those who say no, why do you say no? I guess those who say no are more understandable because there are only n over 100, so what's the likelihood, right? But why do you say yes?
Because it's independent of the number of balls. The probability that you're choosing a particular ball is 1 by n, right? So even though it's a multiplicative constant factor, so it wouldn't change the probability by that one.
I don't understand. So
You're choosing whenever you choose a ball goes to a bin, it's with the
Yes.
same probability, right?
yes, so it's 1 by n, yeah.
So the number of balls that you throw in do not affect the way that you choose which one you choose. So if you think about it that way, it's just a constant that you're multiplying with the probability. So the order of the should be in the same order.
Right, so I guess what you're saying is essentially that if I try to do the same calculation I did on the right there, okay, so if I had n balls, then I have 1 over n squared, that's still the same 1 over n squared. Okay. So here, suppose I call this m. Okay. Now, if I picked 2 balls and ask what is the likelihood that these 2 went to a specific bin, okay. So that would be something like 1 over n squared. And if I say what's the likelihood that there existed 2 things, then there is an m choose 2 that comes in. Okay. This is the likelihood that one bin gets 2 balls, right, in this case. Okay. And now if m is n over 100, this is still n by 100 squared by 2, right? So this is m squared by 2n squared. Okay, this is asymptotically equal to this because m choose 2 is like m squared by 2. It's m times m minus 1 by 2, but m minus 1 is like m. So this is what we have. And if m is even n over 100, this is still some constant. Okay, so there is some constant probability that it gets 2 bins. by 100 is bad. What about m equals root n? So what would this probability be, right? So this probability would then become roughly 1 by n. Okay. So if I took one bin and asked what's the probability that this gets a collision, then it's exactly 1 by n. Right? That's what this calculation is saying. Okay? But I actually have n different bins. Right? So if you think of them as being independent, then you expect this an event of probability 1 over n to happen with some probability. Right? So you expect like if each bin, let's call a bin bad if it gets 2 balls. Okay? What this is saying is probability that one bin is bad is 1 by n. Okay? And I have n different bins, so you expect that with reasonable probability one of them will be bad. Okay? So this is the thing in probability where if you have even a low probability event, if you have a lot of events, then at least one of them, this bad event will happen. Okay? So, yeah, so this is one reason they give for statistics, right? So often you'll find two completely disjoint things being pretty correlated with each other. And the reason for this is that there are so many phenomena in the universe that if you, with just by chance there will be many things that are just pretty well correlated with each other. Okay, so I forget there's a term for this which I'm blanking on, but it's one of these paradoxes. Alright, so this specific value, so I guess you will work it out in one of the homeworks, but this is what's called the birthday paradox. Okay, so what this says is, the way people usually phrase it is, if you have about 23 people in a room, and if you assume that their birthdays are distributed randomly in this, distributed randomly basically, then with good probability 2 people will have the same birthday. And this is something, sounds like a paradox when you first hear it, right? Because there are 365 days, and what's the likelihood that in a group of just 23 there will be 2 that have the same birthday? Right? So this, you can actually precisely work out this calculation and you get some. Okay, so this root n is actually tight. Might be a small constant, which is why you get this for 23. Alright, so this again shows up often when you are doing some kind of randomized analysis. Alright, so this is one. So you do expect some collisions, not so many, but you expect some. Okay, so going back to the question I asked before. So if you had n balls, n bins again. So now again we are back to this case where you had exactly n balls. Now, what is the number of empty buckets you expect to see? So these are buckets that don't get anybody. Right? So how would you calculate that? What is the probability that, actually firstly, let's try to do this the same way that we did before. Okay, so let's call E is the number of empty buckets. Okay, E is probably a bad name, so let me call it M. Okay, so it's the number of empty buckets. Okay, and what I'm asking is, what is the expected size of M? Okay, so what is E of M? So how do you go about doing this? So when you want to find the expectation of something, what do you really have to do, right? If you want to do it the right way, you'll have to say, okay, what's the likelihood that I have 4 buckets that are empty? And calculating that is a mess, right? Because you're saying, I have to pick 4 different buckets to find what is the probability that all of them are empty. Then I have to take a union over all possible choices of 4 buckets and so on. So this becomes messy. So as I said, when you have to find the expectation of some aggregate quantity, you usually split it up into a sum of random variables. So again, let's write this as expectation of sum over j equals or I equals 1 through n yi, where yi is 1 if bucket I is empty, and 0 otherwise. Okay. So here it's this is actually it's the easiest way to do it, right? So here doing it any other way is actually pretty difficult. So this is one example where linearity of expectation is quite powerful. So you can write it like this, and now we just have to evaluate what's the expected value of yi. So yi is a 0, 1 variable. Okay, so to compute its expectation, we just have to know what's the probability that it's 1. So what is probability that yi equals 1? Or equivalently, this is probability that bucket I is empty. So I'm giving you some fixed bucket. What's the likelihood that it's empty? Yeah.
It's almost 1. It's minus 1 by n over 1.
Yeah, so that's one way of writing it. So it's n minus 1 by n whole power n. But why is this almost 1?
N minus 1 by n is pretty close to 1 for high values of n.
Right, but this is the canonical example, right? So if you have a number less than 1, it could be really close to 1. But if you power it enough times, then it becomes smaller. Okay, so do you guys, how many of you know what this number will be? Calculus 101. So this, I think if I write it differently, you will all remember this. This is 1 minus 1 by n whole to the n. Okay. So n minus 1 divided by n is just 1 minus 1 over n. Right? And this whole to the n. So what is this? So if you have n large, you can actually, I guess, try to evaluate this, but many of you probably know. Okay, so I guess if you don't know it, this number, as n tends to infinity, for n large enough, this actually converges to a constant. Okay, and the constant turns out to be 1 over e. Okay, so where e is the Euler constant, it's 2.718. So this actually always converges to a constant. Okay, so that's the cool thing about this. So you would, yeah, and the reason is that even though 1 minus 1 over n is really close to 1, if you power it enough times, it becomes smaller. And if you take to the power of 100n, for example, then it's 1 over e to the 100, which is extremely tiny. Okay, so n is exactly where this transition happens. Yeah. So if you haven't seen this, you should. I mean, go back, look at some basic calculus text, and you will find this. Okay, so this turns out to be a constant. And so what is this saying, right? So this is saying that the probability that some bucket is empty is 1 over e. Okay, it's don't know what this is. This is, I think, something like 0.3 something. 0.36, whatever. And so now how do you compute the expected number of buckets that are empty? So I wrote this down, right? So what is the expected number of buckets that are empty? The probability that each bucket is empty is this. So now you can use linearity of expectation. right? To say that this is just n times this probability. Okay. So expected value of m is n times the expected value of yi for all I basically, and this is n by e. So one thing which I forgot to mention when I was talking about linearity of expectation is that note that these events are highly dependent on each other. Okay? So the probability that yi is 1 is quite dependent on the probability that some other yj is 1, right? So in some sense, if bucket I is empty, you would expect that intuitively a lot more elements go into bucket. I mean, there's more likelihood that bucket j is not empty. Okay? So these numbers are actually independent. I mean, these numbers are actually dependent on one another, but still, linearity of expectation holds. Okay? So that's the power of this, which is it'll take you a while to appreciate it, but this is something to keep in mind. Okay, so that linearity of expectation is a very non-trivial fact if you think about it. Okay. So that's where you can use this. Okay, so to conclude that the number of buckets you expect to be empty is exactly n over e. Okay, and this is all exact calculation. There's no bounds here. Other than the fact that n is large, that's when this number tends to 1 by e. Okay. So, any questions on this? Maybe I'll pause here for a bit because there's a lot going on. Okay. Any questions? So yeah, meanwhile maybe then you can think of this. Okay, so suppose I ask what's the expected number of buckets that have size 10? So what would you guys expect, what would you think the answer is? I mean, I don't expect you to give that number, but what's a guess? Do you expect a linear number to have size 10? Or do you expect a constant number to have size 10, log n? What's the...
It seems like it would
A
get,
good guess. Yeah, so we'll see.
it seems like as that number approaches n, it'll get exponentially smaller.
That is definitely true, yes. But how does it go, right? So yeah, what you said is right. So if I say what's the number of buckets of size k, then we saw that 0 has this n over e, and 1 will have some other number, and so on. So this curve will look, I think it will look like, it will increase and then drop. But it will drop exponentially with k. That is definitely correct. So, but I'm saying what happens at 10? So is 10 out here or is 10 out here?
It's kind of out there.
Alright, so yeah, let's see. Okay, so let's see how to compute this. Okay, and it's very easy. It's just all these calculations you can do the exact same way. Okay, so that's the point I want to make. Okay, so I want to say what's the expected. So again, you define m to be number of buckets of size 10. And I say yi is an indicator variable. This is 1 if bucket I has size 10 and 0 otherwise. Okay. And then you know that m is sum over I yi. So you know that expected value of m is sum over I expected value of yi. And this you can try to compute. Okay. So this is the general way in which you try to, if you have a quantity that seems complicated to reason about, you try to break it up into simpler things. And now each specific I, it's easier to analyze, right? Because you now have one bucket and you know exactly what's the probability of what's the probability that one guy goes here, what's the probability that some other one comes here, and so on. So what's the probability that yi equals 1? Okay, so this is all you have to answer. Okay. So what's the probability that yi equals 1? That there exists there exists 10 different things on the left that go into this. Remember, I'm saying it's exactly 10. Okay. So what I'm claiming you can write a closed form for this. Instead of 10, if I had 2, what would it be? The
1 by n square.
1 by n square is if I picked 2 different things and asked what's the likelihood that these guys go here, right? So what I want is, I'm not saying anything now about these other guys. So what if somebody else also went to that? Then it would not be 2, right? It would be 3. Okay, so you've got to say that these 2 go to the bin, nobody else goes to the bin.
Choose bin out and choose 1 over n.
Yeah, so if you work this out, this is actually straightforward probability calculation. Okay, so this is n choose 10. This is the number of ways in which you can choose 10 things out of this. Times 1 over n to the 10 times 1 minus 1 over n to the n minus 10. This is because these things, so you are picking 10 different indices. You want those guys to go to bin I. You want none of the others to go to bin I. And this you can do this calculation, and this turns out to this. As we just saw, this is roughly a constant, so this is like 1 by e. There's this minus 10, turns out doesn't change things much. And this is what matters. Okay, so, and this is, this again, n choose 10, right? It's, how is it compared to n to the 10? That's what we are asking. And this is like n times n minus 1 times what, times n minus 9 divided by n to the 10 times 10 factorial. And if you believe that each of these terms is roughly 1 and there are only 10 terms, right? So this is roughly 1 over 10 factorial. So in fact, this is true in general for k which is reasonably small. Okay, so for all reasonably small k, you can say that the probability that some bucket has gets k elements is roughly 1 over k factorial. Okay, so this is what you can say. I won't go into that, but for 10 it is 1 over 10 factorial. And now you just have sum over I equals 1 through n of this number. So it's times n. Because we computed the expected value of each yi. And now you just have to add them up. Okay, so that's the nice thing that you get from linearity, that you just add them up. Okay, so expected value of m in this case is roughly n by 10 factorial. Okay. So, and this is a constant, right? 10 factorial is just some constant. And so you actually have a linear number of things that have size 10. A linear number of buckets that have size 10. Okay. So is this clear? Okay. At this point, you could ask all kinds of questions, right? You could say, what's the probability that I have n over 100 buckets of size 10? And you can use Markov to get a pretty good bound. Okay, that would be pretty unlikely. So, yeah. So you guys should think of questions like this and try to answer them. Okay. So in this we already answered. This you can do the same kind of calculation and you get for k small enough to get 1 over k factorial. You get n divided by k factorial. Okay. And this is what says that if you choose k as being roughly, let's say, log n by log n, then this number starts getting less than 1. Okay. So this number turns out to be less than 1. Okay. So this again, if you don't know, you just have to believe me for now, but the question we are asking is, for what k does k factorial become bigger than n? Okay. This is a well studied thing in math, and then it turns out that the answer to that is log n by log n. Okay. So how many of you have seen this? Whether this is one of these things that some calculus courses do. So you're basically asking what, as I said, what k does k factorial become n? Oh, so no one has. That's maybe I'll put up links to where you can find this sort of things then, because those will be necessary for homework and so on. So it'll be, yeah. But these are all fairly simple to work out, but they involve calculation. Okay, so I can't just do it right now, in the sense I'll lose half the thing. Yeah. So it's one of these things better for you guys to just see at your own leisure. Okay, so it turns out if you choose this, then the expected number is less than 1. Okay. So suppose we agree to this. Okay, so suppose we say that you have k to be this big. Okay, so then what are we saying? We are saying that expected number of bins with more than let's say 2 log n by log n balls. Okay. So this is actually much less than 1. Okay, so if I added this 2 here, and I mean, if you continue this line of thought, you can show that this is actually less than 1 over n. Okay, so this is much smaller than 1. So what it's saying is the number of bins you expect it to be much smaller than 1. Okay. And how could that be, right? So this is the expected number of bins. So this is an integer, right? The number of bins is always an integer. It's 0, 1 through something. Okay. And how could the expected value be much smaller than 1? Okay. Do you understand the question? So this is the number of bins is always an integer. And it takes values 0, 1, 2, so on. We are saying the expectation of this random variable is actually 1 by n. So how could that be? Yeah, it will be 0 with very high probability, right? So that's the only way this can happen. So for instance, if you want a value 1 over n, you could have 0 with probability 1 minus 1 by n and 1 with probability 1 by n. That's when you get expectation of 1 over n. So, but in particular, this implies that you are 0 with very high probability. Okay, is that clear? So if the expectation of an integer valued random variable is much smaller than 1, okay, then you have to be 0 with very high probability. Okay, so that's what this is doing. Because even if you are 1 with any probability more than 1 over n, then your expectation will actually be higher. Okay, so this is another standard way of showing that of computing the probability that it's 0 in some sense. Okay, so because this implies that probability that there are no balls there are no bins size more than this number is at least 1 minus 1 over n. So if you don't see this, I encourage you to just work it out. So what this says is, so I compute the expected value of the number of bins that have this size. That expected value turns out to be much smaller than 1. Therefore, you conclude that the number of bins must be 0 with very good probability. Number of bins being 0 basically means there are no bins which satisfy this property. And what this says in particular is that the max bucket size is smaller than 2 log n by log n with probability at least 1 minus 1 n. Okay. So that's what this implies, right? Because if there are no buckets of size more than this, then it means that the max bucket size is smaller than or equal to this, and that happens with very high probability. So this is the common way you argue about this kind of max bucket size and so on. So one takeaway from this is that this happens to be tight. Okay, so as this, I don't think it will be regular homework, but I will point you to it. Okay, so this turns out to be tight. Okay, so if you have n balls going into n buckets, then it turns out that the max bucket size is actually roughly log n by log n. So this is very important from a load balancing point of view, right? Because what this is saying is, if you have n tasks and n people, and you randomly assign, then this is saying that n over e fraction of people will actually be jobless. I mean, they don't have anything to do, and some guy will have log n by log n tasks to do. Okay? So which could be relatively big. So this sort of thing is good to keep in mind. Alright, so the other thing I wanted to do was union bound. So let me do this. Okay, so this is fairly simple. So how many of you have heard the word union bound? A few. So alright, so let's do this because I want to, in some sense, so this is one way of finishing this up. Okay, so I want to also do this thing where so we've seen linearity of expectation, right? Where we said that you have a random variable and you express this as the sum of different simpler random variables. Okay? So this sort of analysis is powerful and it's ubiquitous in probability. Okay, so basically one similar scenario is you have some event that you're interested in. Okay, so you have some event E, and you want to show that it is very unlikely to happen. Okay, so this is an event, and want to show it's unlikely. So one way to write this is to say that you have E and you write this as A1 union A2 union so on up to some, so you have a bunch of events, you can divide into how many ever you want as per your convenience, and now you bound the probability of these guys. So formally what this says is if you have events like this, then the probability of E is smaller than or equal to sum over I through from 1 through k of probability of k. So this again is very simple to state and this is almost trivial, right? So this is intuitively extremely trivial. But this turns out to be very powerful. Okay, so I wanted to do this proof of the same fact but by appealing to this, but maybe we won't have time. But this is just something to remember. Okay, so we'll find other uses of this. So might as well wait until. So this is So if there are two things you should remember from today's class, it's this notion of union bound. So where you have an event, and you say that it's the union of these kind of events, and you bound the probability of each one, and then you have a sum of these things. And the linearity of expectation. So you want to find the expectation of a random variable, right? As a sum of simple things, and usually those simple things will be 0, 1 random variables, and there it's actually equality. Okay, so if you have x equals x1 plus xk, then Ex is exactly equal to sum over I Ex. And for this we've seen some powerful uses. Right? So, and this is true no matter how correlated these xi's are. Right, that's the nice. So we will stop here.